Welcome to the Explainer. Today we're diving into part one of a really fascinating engineering puzzle. We're going to explore how the actual physical shape of a massive offshore rig completely and totally dictates its internal electrical plumbing.
Right off the bat, we're looking at a huge core paradox in offshore drilling. You've got a semi-submersible, which essentially floats on these giant submerged pontoons. And then you've got a drill ship, which acts and moves much more like a traditional ship that can propel itself across the ocean. These are two wildly different floating vessels, but here's the kicker. They do the exact same job using the exact same gear. So the electrical architecture, it basically has to bend to fit the hull it's sitting on.
Okay, let's dive into this a bit deeper. Before we can even talk about the power layout, we need to understand what we're actually powering. Regardless of what kind of hull they're sitting on, both of these rigs use identical, massive mechanical components. You've got the towering derrick, the traveling top drive that's rotating the drill string, and those absolutely massive mud pumps holding back formation pressure. All of this heavy machinery requires a ridiculous amount of highly controlled electricity.
So how does a semi-submersible handle this massive power demand? Well, because a semi-sub relies on buoyancy and stability while partially submerged, its entire design philosophy is all about managing weight and gravity.
Form completely dictates function here. On a semi-submersible holding its position out in the ocean, you want your heaviest equipment placed as low as physically possible. Why? To fight the pitch and roll of the waves. Because of this, the heavy power generators and main switchgear sit way down low in the pontoons or the lower columns. That means the power cables run straight up through the columns to reach the drive rooms near the drill floor. The end result is that your cable runs are vertical and honestly relatively short. Now let's contrast that entirely with the drill ship. A drill ship acts and is built much more like a conventional self-propelled vessel. It doesn't have deep pontoons. Instead, it has a long, streamlined, horizontal hull. I absolutely love this apartment layout analogy. The exact same drilling furniture is crammed into two completely different floor plans. A semi-sub is basically a townhouse. You've got your heavy generation on the ground floor, and your drive rooms are stacked vertically right above it. A drill ship, on the other hand, that's a shotgun house. Everything is arranged in a straight line, with much longer hallways connecting all the rooms.
Now, what's really interesting about this shotgun house layout is that it creates a huge chain reaction of engineering headaches. With the engine room typically way in the back and the derrick situated toward the middle, power has to travel horizontally across the entire length of the hull. These much longer cable runs mean engineers have to specifically design around major voltage drops, and they have to find real estate for switchgear rooms along the way.
Let's see how this builds into another challenge, because space and long cables aren't the only problems here. These electrical architectures have to defeat a relentless main villain, the incredibly harsh, corrosive marine environment.
Time for a quick pop quiz. Lots of drill ships specify water-cooled variable speed drive cabinets instead of the standard air-cooled ones. Now, why on earth would you want to introduce water cooling into a room full of live, high-voltage electronics out on the ocean when air cooling is so much simpler? Take a second and think about what air cooling actually means out there.
Did you guess it? Air cooling means you are actively drawing ambient marine air, which, by the way, is absolutely packed with humidity and corrosive salt, straight across your live critical electronics. That's a recipe for disaster. By specifying a water-cooled cabinet, the enclosure can be completely sealed tight, stopping that salt air ingress dead in its tracks.
And this brilliantly illustrates exactly how this works in practice. Inside that sealed cabinet, a closed freshwater loop is what actually cools the sensitive electronics. That warm fresh water then rejects its heat through a plate heat exchanger to the seawater, which is drawn from the hull. So the salt water takes the heat away, but it never ever touches the internal gear. Pretty elegant solution, right?
So the crucial point we want to take away here is this: physical constraints completely rewrite electrical reality. We have two floaters doing the same job. The semi-subs put their generation low in the hull for stability, which gives them short, vertical cable runs. The drill ships run power horizontally with long cable runs and rely heavily on sealed, water-cooled drives to fight the marine air. It is literally the exact same drilling package, just with totally different electrical plumbing.
Now, both of the hulls we just talked about are floaters, but what happens to the electrical layout when a rig doesn't float at all and instead stands directly on the seabed on its own legs? How does a compact, non-floating footprint change the rules all over again? We are going to tackle that fascinating shift in part 2 of this explainer. See you then.